Hello guys, and welcome to this video in the series explaining the Exploding Dots project. So in this video, we're going to take a little step back from high school, back into elementary to middle school math, dealing with decimals. So before we were dealing with a 10 to 1 machine, basically converting all of any numbers such as 257 into these dots, and sometimes anti-dots with subtraction as such. However, we see that we just continue on this way. But what happened when we're going the other direction? Well, actually, within numbers, we can actually express this. Instead of having simply the number continue this way, it also continues the other way. So let's draw another machine right here. It's a 10 to 1 machine. And then we have this machine over here, which continues on forever that way. Let's just fill in the boxes and separated by a decimal point. So let's say we want to write, let's say the decimal 1.57, right? We have 1.57. Well, let's look at the values we assign to each box again. So we had 1, 10, 100, or when we looked into it algebraically, we saw that this would be whatever base we're in, so 10 in this case. 10 squared, 10, so that would be just 10 to the power of 1. And what would this be? Somehow we have to do through exponents to get 1. Well, this would have to be 10 to the power of 10 to the power of 0, pardon me. So we know this because it was called, to get to the next box this way, we must multiply by 10 because we're asking for 10 sets of such. So going back the other way, we simply divide by 10 in order to get the value, so that would be 1. Well, what would this box be? It has to be 10 to this number minus 1, right? That would be 10 to negative 1, 10 to negative 2, 10 to negative 3, 10 to negative 4, and so on to infinity. Well, this is equivalent to 1 over 10, 1 over 100, 1 over 1,000, 1 over 10,000, and so on. So when we write 1.57, what we're actually doing is just a series of fractions. We have 1 plus 5 over 10 plus 7 over 100. It's as simple as that. Now, if we're going to try expand our use of this 10-1 machine to, let's say, addition. Let's say we're trying to add 1.57 plus 3.6542, right? So we can do the same as we did before. Let me just make these dots for you guys. So we'd start off with 1.57. We'd have 1 dot here. We'd have 5 dots here. And we'd have 7 dots right here. Then we'd have to add 3.6542. So we'd add 3 dots here. We'd add 6 dots right here. We'd add 5 dots here. We'd add 4 dots here and 2 dots here. Alright, so adding that becomes 4. That would become 11. This right here would become 12, I believe. Yeah, 12. 4 and 2. Obviously, we have these are greater than 10, so we have to explode them across. So we explode 10 dots from here to make it 1, and we add 1 here, so that's going to be 5. Then we explode 10 dots here as well, and we're left with 2. We add another 1 here. So then what it would result in would be 5.2242. Quite simple stuff. Now, what do we do when we subtract? Well, this is really the same as we had before with all of our other systems. Let's say we do let's use these numbers again. Let's have 3.6542 minus 1.57, and let's add 3 there, right? So let's put 3 dots here. Let's put 6 dots here. Let's put 5 dots here. Put 4 dots here. Let's put 2 dots here, right? Now, if we're subtracting that, we're actually adding negative 1.573. So then let's add those as antidots. We have 1 there, we have 5 here, we have 7 here, and we have 3 here, right? So these cancel out, which leaves us with 2. All of these cancel out to give us 1. Ooh, we get to here, and we're left with 2 antidots. And here we're left with 1 dot and 2 dots because we didn't have any antidots in there. So now we go back to what we used in simple subtraction. We simply unexplode that dot into here, which would give us 10 dots extra here, and move that out. And simply we connect them. We ensure that the antidots cancel out the dots that we had there. And so we're left with 2.0812, I believe, yeah. Now, one of the other things that we use for fractions that were taught all the way back in primary school is this concept of moving the decimal place when we either multiply or divide by 10, right? We're taught that if you multiply by 10, then the decimal point simply shifts over 1 space. And if we divide by 10, then we simply shift the decimal place to the left 1. Well, this isn't actually how it happens. So let's take our number again, 1.57, right? 1, 5, and 7. Now what happens when we multiply by 10? Well, these dots right here, they get multiplied by 10. So then this becomes 10 in here, this becomes 50, this becomes 70, and then we simply explode them across so that all the boxes are less than 10. So this one right here explodes to give 1. This one right here explodes to give 5. And this one right here explodes to give 7. So it's not actually the decimal place that's moving, rather it's all the numbers surrounding it that move up. It's the same with division, where we simply divide by 10, where you're looking for groups, and it simply shifts all the numbers to the right. Now, if we deal with fractions, then it's always going to become expressible as a decimal. So let's take, for instance, let's take the, I'm trying to think with the space here. Let's take 6 over 7. I think we're going to have to add, we're going to have to add more space. Let me just add a box here. We have a dot there, and then we have our other box here. And just erase these points these values right here. So, of course, it's a 10 to 1 machine. And so 6 over 7, that's actually equivalent to 6 divided by 7 by definition. So what we can do is we take 6 of these dots, right? And what we can do is we simply unexplode all of them, right? So let's get 60 dots here in place of these 6 right here, right? And in these 60s, we're simply looking for 7. So then 7 goes into 68 times, right? Which leaves a remainder of 6, I believe? No, 4. Leaves a remainder of 4. Then we explode these over. We have 40. Let me just double check that my math is correct. Yeah, because that's 54 right there, I believe. Yeah, 56 in here, then 4, yeah. So we have 40 here. So then we need to see how many times 7 goes into 40. Well, that'd be 5 times, so it's 35, which leaves a remainder of 5 right there. And then we get 5 here. So we explode over here, 50. Well, that's going to be 7 times, so obviously. We have 7, we have a remainder of 1. Then we get to 10 here. Well, that goes into once, I believe. Wait. Yeah. 1 here. And so we get left with a remainder of 3, right? Because 10 minus 7. Then we explode this over again. So we're going to get that 4. We're going to have 2 there. 20. which 7 goes into twice, which leaves 6, and then x equals 60. Aha, see what we're getting here. Now we get 60, but this is the same as over here, which is 8. So we can actually write this as 0.857142 repeating. Now there's many different ways you can notate this. This is just one example. You can also, instead of putting the line over, you can write as 857142 ... and so on. But by definition, all of these fractions must result in a decimal, which will either be repeating or it's going to finish. Let's say, for example, 1 over 4, it's going to be 0.25. However, there's repeating 0 at the end of it. Now, the reason why this happens is if we actually look at what we're dealing with, we're actually dealing just with the remainders of all of the numbers. Well, if we're in a base 10 machine, then there's only going to be 10 possible remainders if you include 0. If you don't include 0, then there's 9 possible digits and the remainder can be. So there's going to be 9 possibilities for each one. So each of the decimals will repeat at some point, thus will be able to be said to be or expressed as a repeating decimal. Now then, this brings on to the case, what about irrational numbers? Because rational numbers are said to be able to be expressed as a fraction. Well, many people would simply say, oh yeah, pi is an example, or that's a very poorly drawn pi, but pi is an example of an irrational number. Root 2 is an example of an irrational number. But that just means that it cannot repeat or it cannot end. So then we can write that, let's say, we can write our own irrational number. Let's say 0.1011 01110 01111 and so on. Now you can probably get any digit that you want using these rules. However, it does not repeat, even though it has a pattern, which makes it irrational. And yeah, that's the video for today.